In Module A1 Objective 4, you're asked to explain how atomic properties influence reactivity and to be able to differentiate between the bond types, the covalent, ionic, and hydrogen bond types, as well as generalize how atoms bond to form compounds or molecules. To begin this topic, we need to revisit the atom, and we had discussed atom in the previous objective. We know that the atom consists of a nucleus that holds subatomic particles, namely the proton and the neutron, and that the electrons are found within the electron cloud orbiting the nucleus. It is the electrons that determine the reactivity of an atom, and we'll define, hopefully, reactivity as we work through this objective. We note that the electron cloud contains shells, or energy levels, and each energy level can hold a maximum amount of electrons. For instance, the first energy level, let me make a little table here. Energy level, okay, the first can hold can hold 2 electrons. If you look at lithium, for instance, right here, lithium has an atomic number of 3. That refers to 3 protons in the nucleus and 3 electrons in the electron shell or electron cloud. And the first energy level, this first shell, can hold 2 electrons, and that's it. So here we have 1, 2. The second energy level can hold 8 electrons. And in fact, the second and the third can both hold 8 electrons. So in the case of lithium, the last electron is located in the second shell. And if we were to look at a larger atom, such as neon, if you look at the periodic table of elements, you will see that neon has an atomic number of 10. Therefore, it has 10 protons and 10 electrons. As we place the electrons within their shells, the first shell can hold a maximum of 2. So we have 1, 2. The second shell and third shell can each hold a maximum of 8. In the case of neon, there's only 8 electrons left, and they're all in the second energy shell. The thing about atoms is they want their last energy shell, whichever it may be, to be filled. And we refer to that outermost shell as the valence shell. And it's this shell that really indicates or determines bonding. Chemical bonding involves either the sharing, gaining, and losing of electrons, all from that valence shell. And there's 3 major types of chemical bonds. We're going to consider the ionic and the covalent bonds, as well as the hydrogen bonds. Ionic bonding is the attraction between the cation, we'll define this term in a bit, and the anion. Covalent bonds is a sharing. It's a bond formed through the sharing of electrons, and we'll address hydrogen bonds when we get there. Alright, so why do atoms bond? Well, they do so to form molecules or compounds. Molecules or compounds. In case of molecules, you have 2 or more atoms that are joined by strong bonds. And in the case of compounds, you have 2 or more atoms of different elements that are joined by strong or weak bonds. So there is a difference. In the case of compounds, they have to be of different elements. Compounds are all molecules, but not all molecules are compounds. And just to give you an example, H2, this is a molecule. It is two or more atoms joined by strong bonds. H2O, on the other hand, is both a molecule and a compound because it contains different elements. You have oxygen as well as hydrogen. To test that knowledge, let's look at some examples, and I need you to indicate whether you have a molecule, a compound, or just an atom. So let's look at this right here. This is nitrogen. Is this a molecule, a compound, or an atom? Well, because it does not contain different elements, this is a molecule. In fact, we have a molecule here and here. In terms of the compounds, again, compounds is when you have two or more atoms that are bonded together, but the atoms have to be different. So here we have a compound, and the rest are going to be just atoms, single atoms. Alright, let's consider ionic bonds. Ionic bonds occur when you have one atom that loses one or more electrons and becomes a positively charged cation. And I will show this in a minute. The other atom gains those electrons, becoming an anion, which is a negatively charged particle. And the ionic bond forms when you have an attraction between the cation and the anion. Let's consider sodium. We've already seen sodium. We know that the chemical symbol for sodium is Na. It has an atomic number of 11. And what does that atomic number indicate? Well, it indicates the number of protons in the nucleus. It also indicates the number of electrons if the atom is stable. So let's look at placement of those electrons. If we consider the energy shells, or the energy levels or the shells around the nucleus of sodium, we know that the first shell can house 2 electrons, and there we've placed 2. If we subtract 2 from 11, that leaves 9 electrons left for placement. The second energy level can hold 8 electrons, and you can see that all 8 of these have been placed. And if we take 9 minus 8, that leaves 1 electron. And that last electron is going to go into the valence shell, the third energy level. Now, what do all atoms want? They want a filled valence shell. So how close is sodium, this sodium atom, to having a filled valence shell? Well, one of two things can occur. It can either gain 7 electrons, that would fill that third energy level, or it can lose 1, and the second energy level will then become the valence. Is it easier to gain 7 or lose 1? It's intuitive. It is a lot easier for sodium to lose 1 electron than it is for it to gain 7. So, if sodium were to lose 1 electron, it would then become a cation. So, if sodium, I'm going to forward one slide so that I can write. So if sodium were to lose 1 electron, it would become an cation, or a cation. Let's see how that happens. Let's redraw our sodium atom. Here we have sodium. We know that there are how many protons in the nucleus? 11 protons. And in the first energy shell, we have 2 electrons. 1, 2. In the next energy shell, we would have how many? 8. So, if we were to total, we have 11 positive charges, 11 protons in the nucleus, and we have 10 negative charges within the electron shell. What that gives you is it gives you an overall +1 charge, and positively charged ions are called cations. And that is what happened to sodium. It is now a positively charged cation. That's kind of redundant. It's a positively charged ion, which is a cation, would be more precise. So let's go back one slide to our situation and let's consider chlorine. Chlorine has, let's count how many electrons are in a chlorine atom. We have 17. So there's 17 protons in the nucleus of chlorine, and there is going to be 17 electrons. Let's look at the placement of those electrons. We know that the first energy level has 2 electrons, and we see them here. Here's 1, and here's 2. The second energy level has a total of 8. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. And the third energy level has the remaining, which are 7. 1, 2, 3, 4, 5, 6, 7. So what do all atoms want? They want a filled valence shell. Is the valence shell of chlorine filled? The answer is no. It only has 7. It can hold 8. Therefore, one of two things can happen. It can either lose 7 electrons or gain 1. In the case of the chlorine atom here, it is much easier for it to gain 1 electron. When it does, it becomes an electron acceptor. It is actually obtaining that electron from sodium, which is the electron donor, and it becomes a negatively charged ion or an anion. Let's write that out. So if chlorine were to gain 1 electron from sodium, it would become an anion, or a negatively charged ion. If we were to do the math, we know that chlorine has 17 positive protons in the nucleus, and it now has 18 negatively charged electrons in the shell, and that gives you an overall -1 charge, and any negative ion is called an anion. So what does that mean for sodium and chlorine? Well, in the case of sodium chlorine, it is the attraction between the cation and the anion that forms the ionic bond. And that's what you have here, the formation of an ionic bond. An ionic bond forms when one atom donates an electron to a second atom, which is the electron acceptor. You get the formation of a cation, which is a positively charged ion, and an anion, which is a negatively charged ion, and you get the formation of an ionic bond. Let's consider covalent bonds. Covalent bonds involves the sharing, and that is the difference. The sharing. This is the one word that differentiates these two. It is the sharing of pairs of electrons between atoms. You have a situation in which an electron is donated by each atom to make a pair of electrons. And there's several examples here. What I'm going to do is advance one slide to an empty page so that we can draw this out a bit better. There's some good English for you. Let's consider the covalent bonds that form in a water molecule. So let's consider the water molecule. We know that water, the chemical notation for water is H2O. And if we look at the actual molecule, we find that it looks like this. It's kind of bent in shape. So here's our H2O. Let's look at those atoms specifically, and let's start with the oxygen. If you go back to the periodic table of elements, you will notice that oxygen has an atomic number of 8. So here is our oxygen atom nucleus, and there's going to be 8 protons, and we need to place the 8 electrons around. How do we do that? Well, we do that through shells. In the first shell, we have 2 electrons. 1, 2. That leaves how many in the second shell? Well, hopefully you've come up with 6. 6 electrons. What do all atoms want? They all want a filled valence shell. In this case, it is not filled. We have 6. One of two things can happen. You can lose the 6, or you can gain 2. In the case of oxygen in this situation, it is much easier to gain 2. So let's see how it can gain those 2. Well, to understand that, we also have to consider the hydrogen. And hydrogen each have 1 proton in their nuclei. And in their first energy shell, they're going to have 1 electron. Those hydrogen atoms, what do they want? They want a filled valence shell. Is their valence shell filled? The answer is no. It needs to either gain an electron or lose an electron. So we have an oxygen atom that needs 2 electrons to fill its shell, and we have 2 hydrogen atoms which each need 1 electron to fill its shell. What you get is a sharing. You get a sharing. If the hydrogen atom here shares its electrons with the oxygen, both atoms are going to have full valence shells. And the same thing on the other side. So this is a very nice match. And covalent bonds, I'll back up one slide, involve the sharing of pairs of electrons between atoms. You get a situation where the electron, 1 electron is donated by each atom to make a pair. If you have a sharing of 1 pair of electrons, it's called a single covalent bond. We have that here, 1 pair of electrons. If 2 pairs of electrons are shared, you have a double covalent bond, such as that we find in oxygen, or O2, CO2, or NO, nitric oxide. And there's even situations in which you have the sharing of 3 pairs of electrons and the formation of a triple covalent bond. That leaves hydrogen bonding. Hydrogen bonding is the bond that forms between adjacent molecules, not atoms. And I'll even highlight that for you. The bonds between adjacent molecules not atoms. This hydrogen bonding involves slightly positive and slightly negative portions of polar molecules that are attracted to one another. And for that slightly, I'm going to give you a symbol. And that is the symbol for slightly, and you see it here. This symbolism equals partially, actually. And we would read this as partially positive. We would read this as partially negative. So it is the attraction between molecules that have a partially positive side to them and a partially negative side to them. I'm going to jump ahead one slide to a blank, and I'm going to redraw molecules of water. These are all water molecules. What is the chemical signal for water? H2O. You basically have an oxygen attached to two hydrogen atoms. And here I've basically drawn their nuclei. So if you remember, the atomic number for oxygen is 8. So there are 8 protons in the nucleus of the oxygen. And each hydrogen has 1 proton. So what do we have between the oxygen and the hydrogen atoms? We have a bond. And what type of bond is that? I'll give you a hint. It is the sharing of pairs of electrons, covalent bond. And what we have in those the covalent bond, it's basically the interaction between the valence electrons. Now let me ask you this. If you were an electron and you are a negatively charged particle, what are you attracted to? You're attracted to the positive charge within the nucleus of the atoms. So in this situation here, you have an electron that is being pulled towards the nuclei of atoms, specifically the protons. In the case of oxygen, you have 8 protons. In the case of hydrogen, you have 1. This little electron is going to kind of hang out closer to the oxygen than the hydrogen because of the 8 positive charges that are pulling it towards the nucleus of that oxygen atom. And what you have is you have the formation of a polar bond, or a polar molecule. And in a polar molecule, one end of the molecule, and I'm going to circle one end, this end of the molecule, it's kind of negative. It's a partially negative charge because the electrons are all being pulled towards the nucleus of that oxygen atom. And the other end of the molecule, it's kind of positive now because of the placement of those electrons. So this forms a polar molecule, one in which you have one end of the molecule partially negative and the other end partially positive. In the case of hydrogen bonds, and I'm going to back up one slide, hydrogen bonds is basically the attraction between the partially positive end of a polar molecule and the partially negative end of another polar molecule. And here we have water again. The very large red sphere represents oxygen, and the 2 smaller blue spheres are the hydrogens. And we even have the notation. Here's the partially negative oxygen side of the molecule, if you will, and the partially positive sides of the hydrogen molecules. And the partial negative side of one molecule is going to be attracted to the partially positive side of another molecule. And all of these attractions are hydrogen bonds. Hydrogen bonds are relatively weak compared to ionic and covalent. In fact, if you were to look at the bond strength, we would see that covalent is stronger than ionic, which is stronger than hydrogen bonds for bond strength. So that is hydrogen bonding. It is the attraction between the partial positive portion of a polar molecule and the partial negative portion of another polar molecule. It is the hydrogen bonding within water that creates surface tension. I think we've all experienced a leaf falling from a tree and landing or floating on the surface of a pool of water. Why doesn't that leaf sink? Well, the polar bonds within those water molecules create a pretty strong surface tension. It allows leaves not to sink. It allows water striders to skate across the top of water. So hydrogen bonds, even though they're relatively weak, if you consider the number of hydrogen bonds that form in a pool of water, it really adds up, and it becomes a very prominent support structure. Okay, the last slide of this objective really deals with states of matter, and as we noted earlier, matter comes in three states. We have the solid, the liquid, or the gas. And if we were to consider let's consider water. What is the solid form of water? Well, most of you would agree that the solid form of water makes ice. So here, if we have this representing an ice cube, we know that an ice cube, as a solid, has constant volume and constant shape. The volume of that cube does not change, nor does the shape, as long as it remains a solid. If we were to subject that ice cube to heat, we would get the liquid state of matter, water. And water has constant volume, but the shape changes. If you were to take a cup of water, and if you were to physically measure out 1 cup of water, that volume would never change. But the shape can. I can pour it into a bucket, I can pour it into a wine glass, and the shape would continually change, but the volume would remain the same. And that is the property of the liquid state of matter. In terms of the gas state of matter, you get a change in both the volume and the shape. If we were to subject that water to heat, you would end up with water vapor, and that would be the gaseous form, the gas form, the gas state of matter. And the water vapor, the gas, can change volume and shape.